Yesterday I taught you about a new law called Coulomb's law, which reminded us a lot of Newton's law of universal gravitation that we learned back in Physics 20. The equation for Coulomb's law, F is equal to KQ1 Q2 over R squared, looks an awful lot like the equation for Newton's law of universal gravitation, Gm1 m2 over R squared. There was an experiment performed by a man named Cavendish in the context of Newton's law of universal gravitation to find the gravitational constant. In the context of Coulomb's law, Coulomb actually performed a real similar experiment to derive this equation, to get this equation that had never been established before. This is what the experiment looked like. He's got a string hanging from the top of a box. On the end of that string, he's got a little rod, and on each end of that rod, he's got a little mass. Object number 1 has a certain charge. Object number 2 doesn't really matter. The other end doesn't really matter. Doesn't have to be charged at all. We bring another object that we're going to call charge 2 nearby charge 1. The distance between those two charges is going to be r. And Coulomb can find the value of r pretty easily. He just measures it with a ruler or some other measuring device. Pretty easy to find the distance anyways. He's able to find not the value of Q1 and Q2, but the relative value. He can manipulate both Q1 and Q2 simply by touching them against neutral objects. If you touch Q against neutral, then the Q becomes a half Q. And then if you touch a half Q against neutral, it becomes a quarter Q. If you touch a quarter Q against neutral, it becomes an eighth Q, and so on. He doesn't know the actual charge in coulombs, but he does know how the charge is changing. He's manipulating the charge without knowing exactly what the value of the charge was. Now, he's also able to find the value of the force, the attractive force or the repulsive force that acts between charge 1 and charge 2. How does he do that? How does he measure the force that's acting on charge 1 here? This is where the torsion balance experiment, the name of it, comes in here. What is it, Parker? Yeah, the torsion balance experiment, the twisting balance experiment. Torsional means twisting. So when we talk about the torsion balance experiment, we're talking about the twisting of the string. That's what's relevant here. The amount of force is measured by how much this string actually twists. So if it twists this much, 3.2 degrees, let's say, then it must have been a force of x. If it twists 5.1 degrees, then it must have been a force of y, and so on and so on and so on. He's able to measure all 4 of these variables. And then he does, with that ability, he does 3 experiments. In the first one, he manipulates the value of Q1, and he sees how the force responds to that. Then he manipulates Q2, he sees how the force responds to that, and then he manipulates R, and he sees how the force responds to that. Does this ring a bell from yesterday? Yes? What shape of graph does he get when he plots this graph, F versus Q1? What is it? It's linear. It's a straight line. What about when he plots force versus Q2? It's also linear. This one, force versus R, was? So in the first one, as Q1 goes up, then F goes up. F is directly proportional to Q1. In the second one, as Q2 goes up, then F goes up. They're directly proportional to each other. In the third one, as F goes up, F goes, no, F goes down. As R goes up, then F goes down. This graph could be represented by this equation, or it could be represented by this equation. It's difficult to tell just with the naked eye of looking at the graph. Turns out in this experiment, it will be represented by this equation. F is related to the inverse of the square of the distance. Coulomb puts these together, and when he does, he ends up getting F is related to Q1, F is related to Q2, and F is related to 1 over R squared. If it's related to all those things, then it's got to be equal to a constant times those things. The constant being 8.99 times 10 to the 9 Newton meter squared per Coulomb squared, versus the constant in gravity, which was 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Now, these two equations have a lot in common. They also have differences. The Coulomb's law equation, Newton's law of universal gravitation, they're both what we call inverse square relationships. It means that F, in both cases, is inversely related to the square of the distance. They're both inverse square relationships. The magnitude? Well, Coulomb's law we established yesterday was a big force versus gravity, which of the four fundamental forces is the smallest one by quite a bit. How do we remember which one is the smallest one? The constant. We look at the constant. Gravity is 10 to the minus 11. Coulomb's law is 10 to the positive 9. That's not why the electric force is stronger than the force of gravity, but that's what helps us to remember that the electric force is bigger than the force of gravity. Bigger constant, bigger force. And finally, Coulomb's law can be attractive or repulsive, whereas gravity can only be attractive. Why? Why is the difference? Well, you can have two types of charge, positive and negative. How many types of mass can you have? One, positive. You can't have negative mass, right? If you could have negative mass, then maybe, just maybe, you could have a gravitational force of repulsion, but you can't. So there's no point in even thinking about what would happen if you could have a negative mass. All right, let's take a look at an example question here. This is example number 1 that's on your handout sheet that I gave you the other day. This question says a metal sphere, so it's a conductor, with a positive charge of 5.5 and a mass of 2.5, is separated from an identical metal sphere. Get the sense that they might touch each other here, since they tell us it's an identical metal sphere. Maybe not. Maybe not. Negative charge of 2.0 times 10 negative 7 coulombs. I'm going to circle this. Positive charge, negative charge. That might be important. Separated by a distance of 5 centimeters. I'm going to circle that as well because of the non-standard unit. What's the electric force on the positive? What's the electric force on the negative? And what's the acceleration of the positive here? Let's write down some givens. I'm going to say Q1 is 5.50 times 10 to the negative 7 coulombs. I'm going to say M1 is 2.5 times 10 to the negative 3 kilograms. Q2 is, I'm not going to forget that this is negative 2.00 times 10 to the negative 7 coulombs. And R, the distance that separates them, is 5 centimeters or 0.0500 meters. Let's find the force on number 1. Let's find the force on number 2. And let's find the acceleration of the positive charge. Let's find A1. Now, watch what I'm doing for this question. It's going to appear as if I make a mistake. Sometimes I do make a mistake with something, some subtle little thing, just to see if you guys catch it. This time, it's the opposite. It's going to look like I make a mistake, but it's not a mistake. I'll point out what that is in a moment here. We say F is equal to K Q1 Q2 over R squared. K is 8.99 times 10 to the 9. Q1 is 5.50 times 10 to the negative 7. Don't forget the negative 7 there. Q2 is 2.00 times 10 to the negative 7 coulombs. What does it look like I've done wrong here? Missed the sign. That's not wrong. When I'm subbing these numbers into an equation, I don't sub the sign of the charge. Why? Because for us, sign means direction. When I'm subbing numbers into an equation, I don't want the negative to mean two different things. Most times for us, all the time for us, it means direction. Left, down, south. I don't want it to all of a sudden mean something else. In my givens, I wrote it as a negative because it might matter later on that it's a negative charge, but not in the equation. Always drop the sign of a charge in an equation. Now the value of R is 0.050 meters. We square that. And when we do, we end up getting a value here of 3.9556 times 10 to the minus 1 newtons. Now, how many digits should we express this to? 2 or 3? 3. Yeah, why not 2? Because this 2.5 times 10 to the negative 3 is 2 digits. Why do we not express it to 2? Because we didn't use that number. So we express it to 3 digits. 1, 2, 3. Look at the fourth digit. It's a 5. So what do? Round down or up? Round up. Becomes 3.96 times 10 to the negative 1 newtons. There's my answer. The answer for what, though? The force on charge 1 or the force on charge 2? If object 1 applies a force on object 2, object 2 applies an equal and opposite force on object 1. So that's the magnitude of the force on both of them, right? It's an attractive force. We know that because they're opposite charges. So the force is 3.96 times 10 negative 1 on both of them towards itself. Now, what about the acceleration? How do you find the acceleration? Yeah, just about every time this year we are asked to find acceleration, I want you to remember this. The force needs to be with you. The force be with you. Okay, it needs to be with you. And then once it's with you, then just divide it by the mass. So get a force, whether it's a context of electricity and it's an electrical force that we just found, or whether it's a magnetic force, or whether it's some other force. Gravitational force, doesn't matter. Get the force. The force needs to be with you. And then use Newton's second law, A is equal to F over M. Use the unrounded number here for the force, 3.9556 times 10 to the minus 1 newtons, divided by M, which is 2.5 times 10 to the minus 3. Gives us an acceleration here of 1.6 times 10 to the 2 meters per second squared. Somebody tell me why I did 2 digits here for this? It's 1.6, yeah. Why did I do 2 digits for the acceleration versus 3 that I did for the force? Because mass is 2 digits. I used it to find the acceleration. I didn't to find the force. Let's take a look at our second example here now, and that'll be the last one for today. It says the 2 spheres in the previous example momentarily touch each other, and then they're separated by 5 centimeters again. What's the electric force that acts between the 2 charges now? Isn't it the same? Like, we have the same objects, right? Isn't it the same force? It is a trap. Yes, it is a trap. You know me well. What's the difference between this question? What makes this different than the previous question? Yeah. They touched each other, and therefore they balance, right? So we had a charge of 5.5 times 10 to the minus 7. We had another one that was negative 2 times 10 to the minus 7. We add those up, divide by 2. Each one of them becomes 1.75 times 10 to the minus 7. That's Q1 and Q2. They were 5.5 and negative 2. Now they're 1.75, both of them. Now the force is just found by Coulomb's law. It's KQ1, Q2 over R squared. That's 8.99 times 10 to the 9 times Q1, which is 1.75, times, once again, 1.75, because they're both the same, divided by R. The value of R is 0.050 meters, as it was before. Solve for force there. I get 0.110 newtons, or we could have said 1.10 times 10 to the negative 1. That would have worked as well. Completely different force, because our charges are completely different. Just because charge is conserved, the total charge remains the same. Doesn't mean the total force remains the same. Not at all. If it's redistributed, the forces absolutely will change, as they have here. All right, we got a couple more examples, but I'd like you to take a look right now at worksheet number 6. And for now, on worksheet number 6, questions 1 to 6.